So, we have seen how the shear stresses are going to be acting at various points of the cross section under the action of the torsion. There are many applications wherein you find that thin box sections are utilized. They may look like this. You can have a rectangular box sections like this with thin walls, they need not be uniform, or you could have section like this compartmented or section like this compartmented. If you look into this section, it looks very similar to that of aircraft wing, and this could be another section of the aircraft wing. So, this type of sections are utilized in the case of machine tools bed and also aircraft wings, although we have other applications too. When these sections are subjected to torsion, particularly in the case of aircraft, when the wind thrust is not uniformly distributed at the bottom of the wing, you will find that some amount of twisting comes up on the section, and it is necessary to evaluate the magnitude of the stresses. Similarly, in the case of box sections, when there are twisting acting, it is possible to assess the stresses through some approximate method. So, we would like to take up those cases. That particular type of analysis we would like to consider. Let us look into a shaft with this sort of geometry, wherein the wall thickness is varying all over. Let us represent the thickness to be T, and it is of course a variable. Let us also indicate that the torque acting on the section is T. You can imagine that this side is fixed and we are applying a twist on the other end. Under the action of the twisting moment, from our earlier study, we can guess that the stresses are going to act parallel to the boundary. Since the thickness is small, we can consider the stress to be uniform along the thickness direction, and therefore, at any point there will be almost a unique direction of the shear stress which is perpendicular to the thickness. So, the stresses are going to act like this at this point. Similarly, a typical point here would have shear stresses acting like this. Because of the thin section, that we can assume that the stresses are going to be uniform, and it can be indicated by a single value at a point. Let us concentrate on an element. Let us say that we would like to concentrate on this element here, this element. This is the center. On this element, the shear stress will be acting, it is going to act, let us indicate that this is the direction of the shear stress on this element, and thickness here is T. If we consider thickness to be this length is, let us say, ds, ds is the length here, So, the total force that is acting on this element is ds into T into tau, that is the force. This shear stress, if we multiply by T, that gives us force per unit boundary. So, this is nothing but force per unit boundary distance this force per unit boundary distance is known as shear flow. So, its unit is Newton per meter. It is shear flow. We will see more meaning why it is called shear flow. If I take the moment of the force, which is nothing but T into tau into ds, then we have T equal to, let us say that the torque due to this length ds is dt, that should be nothing but tau into T into ds, and the normal distance of this, let us say ON. So, this is ON, that is the moment, and it is in the same sense as the applied torque. If we consider now this ds, ds is this to this point and this is ON, we can write now tau into T half ds into ON multiplied by 2. This expression it indicate half this distance multiplied by height. It is approximately area of this triangle O and this point and this other point. So, therefore, I would like to draw this separately. So, what we have here is this is ds, this is O n. So, this triangle is the area here. So, we can write this thing as a dA twice tau into T into dA. So, the total torque T is equal to integration of T to T into dA over this area. Let us consider this is equation number 1. This is equation number 1. Again, I would like to consider an element of the shaft. Let us consider this element. Let us consider this element. The torque, that shear stress there at this point is going to be acting like this. Shear stress here is going to be acting like this. Let us say that this shear stress is equal to tau 1 here, and the shear stress here is tau 2, and this thickness here is equal to T1, thickness here is equal to T2. Since the shear stresses are acting on this face, on the perpendicular face here, we must have shear stresses acting like this, which is again tau 1, and shear stresses that is going to act here on this face, it is going to be complementary to this stress, and this is tau 2. Simultaneously, we will have the shear stress acting here in this direction, it is tau 1, and the shear stress at this point is going to be tau 2. So, on this face you have intensity of the stress acting in this direction is tau 1, and intensity of the stress acting in this direction is tau 2. So, this element let us consider that it is of length equal to L. So, it is oriented in the axial direction, and let us now try to see the forces, net force on this element in the axial direction. So, if you would like to consider that axial direction is equal to Z, this is our Z direction, then sum of the forces on this element, just take it out and think of it that forces are acting on this boundary which are of intensity tau 1 there, tau 2 there, and on this face we have uniform stress of magnitude tau 2, on this face it is uniform stress of magnitude tau 1, and here again we have tau 1 here, tau 2 there. Now, if I try to consider the forces in the Z direction equal to 0, then forces in the axial direction is due to only this face and that face. This force here L into T2 multiplied by tau 2 is acting in the positive Z direction, and the force on the other face it is acting in the negative direction, it is L again T1 into tau 1. So, these two must sum up to 0, and therefore, what it means is that tau 1 T1 into tau 1 is equal to T2 into tau 2, this is a constant. So, this is nothing but a constant. We have taken two arbitrary points with thickness T1 and T2. So, it is true for any thickness that shear stress at the location multiplied by the thickness is a constant. This, therefore, we can write tau into thickness into tau is shear flow is constant. In fact, this shear flow analogy has been taken from fluid mechanics. If you just consider a pipe whose height, whose cross section is a rectangle of this height and length equal to unity. So, therefore, if you think of a portion like this, so it is a circular sort of pipe and the cross section everywhere is rectangular. If you think of it is, think of that fluid is flowing in the circumferential direction. If the fluid is incompressible, then every section would have the same quantity of fluid, and therefore, it is actually from that analogy this shear flow is borrowed, that it is as if that some quantities of fluid is flowing and that fluid quantity is remaining constant, and therefore, this shear flow is constant. So, that is, it is borrowed from fluid mechanics. Getting back to relation 1, we have T is equal to 2 times T into tau into T into dA, and this is over the whole cross section. If we represent this shear flow to be equal to Q, let us say shear flow is Q, then what we have here, so this is from 1 we have A 2q dA and q is constant. So, therefore, this is q and integration of dA is nothing but A. So, torque capacity is related to shear flow multiplied by this area. What is this area? This area is nothing but the area enclosed by the center line of the, approximately we can take it to be the center line of the cross section. So, center line of this section is nothing but A. So, if we have section like this, it is usually area bounded by the center line. So, therefore, this is the area A. This is the area A. This is known as Bredt-Bath formula. So, we have been able to get the relationship between the torque and the shear flow Q. In many applications, it is necessary to calculate the angle of twist per unit length. So, let us see how we can calculate the angle of twist per unit length. The strain energy in an element du is nothing but half shear stress multiplied by the shear strain multiplied by the volume of the element. Here you will find that shear stress is constant at a particular location on the circumference of the section, and therefore, we can now make use of the Bredt-Bath formula. We can write the shear stress in term, we can write the shear stress, and again we can also write the strain in terms of the torque using the formula Bredt-Bath formula that we have derived. So, therefore, we can now write that this is 2 by 2 into T into A into T by 2 into T into A into G, where G is the modulus of rigidity, into dV. We can write this thing as, let us say, T into ds, and in the length direction is this one. So, this gives us T square 8 A square T square G T ds dl, which is nothing but T square by 8 A square into T into G ds into dl. The total energy is therefore obtained by integration of T square 8 A square T G ds over the boundary, and this L is 0 to L into integration of this, and since we have L can be integrated easily. So, therefore, we have now T square, T is constant and it is 8 A square G, and this is integration of the quantity ds by T. So, U is this one. If you consider that the angle of twist of the whole bar is theta bar. So, theta bar total angle of twist that we can obtain from application of Castigliano's theorem, which is nothing but derivative of u with respect to the applied force, which is torque, and in this case it is du dt. So, we get now theta bar is equal to TL by 4 a square g integration of this quantity ds by t. We like to write this thing theta by L as equal to theta, it is angle of twist per unit length, so we now can write twice g theta into A is equal to T by 2A, T by 2A integration of this quantity over the closed contour. We can write this thing again twice g theta into A integration of T by 2A ds by T. You have already got the relationship between the shear flow and the torque. T was given by 2 times A into Q, where Q is the shear flow. So, we can replace this thing by shear flow Q, and we get now this is Q ds by T, and since Q by T is tau, so we have now tau ds. So, twice g theta into A is equal to the integral of tau over the whole of the boundary. So, this the relationship to find out the angle of twist per unit length. So, we have first relationship we have already indicated Bredt-Bath formula as the relationship which is 1. So, we indicated that thing as 1. So, therefore, this will indicate as 2. We can now write the two relationship T is equal to twice Q into A, that is, let us say again 1 dash. So, this 1 dash and 2 dash are the relation, 1 dash and 2 are the relationships which are sufficient to help us to solve for the shear stress at any point and also the angle of twist per unit length for a given torque. Let us solve some simple problems applying this derivation. Let us consider one example of simple square box sections where the sides are 2a, thickness is T, and we have another round section where the radius is A and the thickness is T. What you are required to is that compare the shear stress, maximum shear stress for the same T. In the second case, you are asked to compare the shear stress for the same angle of theta. Let us now work out the solution. We invoke the Bredt-Bath formula. T is equal to twice Q into A and this is nothing but twice tau into T into A. In the case of thin sections, you can take the cross section. Here in this case it is going to be 4A square and the stress tau will indicate by tau square. So, TSQ is nothing but T by 2 into T and area is 4A square. So, it is going to be T by 8 A square into T. If you consider now circular cross section, then again we will have T is the thickness and A is going to be pi A square. So, T for circle T by 2T, it is pi A square. T by 2 pi A square T. So, if we now take the ratio tau square, tau for the circle T by 8 A square T, 2 pi A square T by T, and this is pi by 4. What you find here, that the shear stress in the case of the circle is going to be same everywhere, and for the square it is going to be higher at the end of the middle of the sides, and this is the stress which is going to be higher. In this case you are going to get stress in the circle to be higher than the stress in the square. So, the stress is going to be higher in the case of the circle. So, TCI is greater than T square. The reason is that the length of the boundary is here, in this case it is 8A, in the case of the circle it is 8A, whereas in the case of the circle it is twice pi A, which is less. So, therefore, the stresses are going to be more in the case of the circle. Let us obtain the solution for the second part. So, this is our solution for the first part. We will now look into the solution for the second part. For that, we make use of the equation number 2, which is 2 times g theta A is equal to tau ds. For the, if we consider now the thickness is uniform here, we can write this thing as Q by T ds, and this Q is constant. So, therefore, it is ds by T, and finally, we have Q is equal to 2g theta A by ds by t. You can now substitute the value. A is given by 4 a square in the case square, and in the case of circle it is pi a square, and this circumference is 8 a in the case of square, and it is 2 pi a in the case of the circle. So, therefore, we can now get the shear flow for the square is equal to 2 g theta 4 a square, and this is nothing but 8 a. So, 2 times 4 a by t. So, we will have g theta a t. And hence, shear stress in the case of the square is equal to g theta into a. Now, for the circle, Q circle is 2 g theta pi a square, and we have 2 pi a by t, and once you simplify it is g theta a into t, and hence we can write tau circle is equal to again g theta into a. Hence, the ratio tau square by tau circle is equal to unity. So, for the same angle of twist, you find that the stresses in the two sections are going to be the same, whereas in the case of same torque we have seen that the stress in the circle is going to be higher. So, we have done the analysis for sections wherein you had only one box. You could have situations where number of segments are there in the box section. How to analyze these problems? So, let us look into the analysis of such sections. Typically, what we are trying to concentrate upon in sections like this, where we have one box consisting of these 4 walls, another box consisting of these 4 walls. The total torque that is acting on the section is T. Let us say that this path or box we would indicate by box 1, and this box which is consisting of the portion, let us say E F A B E is 2, and here it is B C D E B is box 1. Let us assume that the flow which is in this circuit is Q1 and the flow which is in this circuit is Q2. Thereby, we will have a net flow in this arm B E is equal to Q3. For simplicity, let us try to also take these symbols, that length in this particular case BCDE has some thickness which is equal to T1. So, everywhere this thickness is equal to T1, and length, let us say that this whole path is equal to L1 and it is of constant thickness T1. Similarly, EFAB is of length L2 and thickness is T2, and this arm EB is of length L3 and the thickness is equal to, let us say, that is T3, and this thickness is equal to T2. Concentrate on the point E. We would now get, from the consideration of flow, this is the junction wherein you think of it that three branches of a pipe are connected. Flow here coming in is Q1, flow here coming up is Q3, and flow going out in this direction is Q2. So, we have two flows Q1 and Q3 coming towards this point. So, Q1 plus Q3 is the incoming flow and outgoing flow is Q2. So, from the flow analogy we can get from the point number 1 that Q1 is equal to, or Q1 plus Q3 is equal to Q2 or Q1 is equal to Q2 minus Q3. That is equation number 1. We can get this equation also from the fact of, from the consideration of equilibrium at the point E. This is something I would like you to note, that this flow equation is equivalent to the equilibrium equation of an element around the point E. So, let us look into therefore the point. This is the point we are talking about, and our beam is, or the box section, the shaft is going to be in the length direction, it is in this direction. I am trying to just take a portion of the section like this, and let us assume that the flow, since flow is in this direction, it is of magnitude Q1, here it is Q3, here Q2. When I take this section, the thickness here is T1 and the shear flow is here in this direction. So, therefore, we will have a shear stress here. Let us indicate that shear stress is equal to tau 1. Similarly, here the thickness is equal to T2 and the flow is Q2, and hence we will have a shear stress here. Let us say this is of magnitude equal to tau 2. This thickness is equal to T3 and the flow is Q3, and therefore, flow direction is this. We would have a shear stress acting like this, tau 3. If this is the shear stress acting here, then on this face, on this vertical face, you are going to get stress acting like that, and this is also of magnitude equal to tau 1. Here the shear stress acting towards this point is Q2, then on this face which is vertical, we are also going to get stress equal to tau 2. All over this space we have uniform stress of magnitude equal to tau 2. By similar consideration, complementary stresses are going to be around this point directed like this. This is of magnitude tau 2, complementary shear stress here is of magnitude equal to tau 1. Since this vertical face is subjected to shear stress tau 3, this face, bottommost face, is also going to be subjected to shear stress tau 3 and it will remain constant, and this vertical face on the left is also going to be subjected to shear stress of magnitude tau 3. So, the stresses acting on all the faces are now shown here in this diagram. So, this is just around the point E. If you consider the z axis to be oriented along the length of the shaft or the shaft with box section, then the sum of the forces in the z direction must add up to 0. So, if we now write that sum of the forces in the direction z is equal to 0, which are the stresses which are going to contribute to the force in the horizontal direction or z direction. Let us say that this length of this segment is equal to L. So, the forces are going to come from this bottom face, this face at the back, and this is the third face which is at the front. Let us now write this area is L into T2. So, L into T2 is the area, and the intensity of the stress is tau 2. So, therefore, the force is L into T2 into tau 2, and then the other force is nothing but L into T1 into tau 1. So, it is acting in the negative z direction, T1 into tau 1, and from the bottom face, which is nothing but L into T3 into tau 3, it is also acting in the negative direction. So, this is equal to 0, and if you now write that T2 into tau 2 is Q2 minus this is T1 into tau 1 is Q1, T3 into tau 3 is nothing but Q3, and that is equal to 0, which is same thing as Q1 is equal to Q2 minus Q3. See, from the flow consideration, we derive the relationship also, which is here. From the flow consideration, we derive that Q1 equal to Q2 minus Q3. Here the flow incoming is Q1 plus Q3 and outgoing is Q2, and from that we found that Q3 or Q1 is nothing but Q2 minus Q3, and now from the equilibrium we find that Q1 is equal to Q2 minus Q3. So, these two conditions are having some similarity. So, this is nothing but one can interpret this thing as an equilibrium equation, and one can also consider this to be a flow equation. So, we have now one relationship involving the shear flows. Now, in a problem of this type that you have to handle, you will be needed to find out the shear flows Q1, Q2, Q3, and also the angle of twist per unit length. So, there are 4 unknowns and we have to obtain all of them. So far we have been able to get only one relationship. Let us now consider this cell number, or let us say first we consider this cell 1. For this cell 1, we can consider the Bredt-Bath formula, wherein we can write that the torque taken by this flow Q1 is nothing but twice Q1 into the area enclosed by this cell is A1. So, we can write for the cell 1, let us say that the torque T1 taken up is nothing but 2 times Q1 into A1, where A1 is the area of BC DEB. Similarly, since we have the flow in the second cell is Q2, again applying the Bredt-Bath formula, let us say that the torque taken is T2, we can write now that the torque is nothing but 2 times Q2 into A2, where A2 is the area of again this cell 2. Since the total torque is going to be T, we can adapt these two torques and we will get a relationship involving the shear flows with the external torque T. So, if we adapt the two relationship, we have total torque T is equal to T1 plus T2, and this is equal to 2 Q1 A1 plus 2 Q2 A2. So, we have now a relationship involving the flows. One equation is here and the second equation is here. Again, we would like to get back to the consideration of the two cells separately. The whole section is going to rotate as a single unit. If we consider that the angle of twist per unit length is theta, we can write that 2 g theta into A is equal to integral of the quantity tau into ds. If I now consider this cell number 1, we can write now 2 g theta into area of this cell cell 1, that must be equal to integral of this quantity tau into ds. So, we have to take the route b to c, c to d, d to e, and again e to b. A1, of course, it is the area enclosed by the contour B C D E B. Now, let us look into what this integral is finally going to lead to. We have the thickness all over this length is constant and the flow is Q1. So, therefore, the shear stress is going to remain constant from B to C, then C to D and then D to E. So, we can now write that this tau is constant and therefore, this integration is nothing but integration from B to E, which will give us L1 into tau 1, because L1 is the length B C D E. Now, we have to go to complete the contour E to B, and when we are going in this direction, then our flow direction or the shear stress direction is different, and therefore, this portion, since thickness is T3, shear stress is let us say tau 3, which will remain constant, and therefore, this integration of this quantity from E to B would mean equal to L3 multiplied by tau 3. So, twice g theta into A1 is related to L1 tau 1 minus L3 tau 3. This is relationship number 3. We would like to continue the consideration, and now we will extend it to cell number 2. If we now consider the cell number 2 starting from E to F, then A to V, then B to E, again we can write for this cell twice g theta into A2 is equal to integration of this quantity tau into ds. For this closed contour, again you have the thickness constant from E to F, F to A to B, and the flow is Q2. So, we can indicate the shear stress to remain constant, and therefore, this will become L2 into tau 2, L2 into tau 2, and from B to E we are moving in the same direction as the shear stress and flow direction, and therefore it will be now L3 into tau 3. So, the relationship that we have got out of this is 2g theta A2 is equal to L2 tau 2 plus L3 tau 3. This is number 4. So, to sum up, finally from this derivation what we have got are the 4 relationships. We have this condition 1, then torque related to the flows and the angle of twist related to the shear stresses here, and therefore you have the unknowns like 3 shear stresses or 3 shear flows and the angle of twist, and you have 4 equations, you can solve for them. So, this is how we can address the problem of segmented box sections. It is solving problems of this type is a routine application of the relationship, 4 relationships that we have derived here. We would like to illustrate this by considering one example in the next lecture. One point I must tell you that this analysis is approximate, it is not to be taken as exact. The very fact is that the stresses at the corner, we know that stresses at the corner is going to be 0, but in this analysis it is assumed to be non-zero. Furthermore, there is complexity of stress distribution around the point E, but we have approximated. So, therefore, to that extent the analysis is approximate, but it gives quickly some idea about the stresses coming up under the action of some torque on this section and the angle of twist. So, what we have done in the last 2 lectures, we have taken the case of thin sections, and also these thin sections can be consisting of one single cell or it can have multiple cells. In the case of single cell, the solution can be obtained by just using the Bredt-Bath formula and the relationship which relate the angle of twist per unit length to the integration of the product of tau and the length ds along the boundary. In the case of segmented sections, you are going to get an equation from the equilibrium at the junction, and you are also going to get one relationship relating the torque to the shear flows, and then you are going to get 2 or as many relationship as the number of boxes. The relationship will involve angle of twist and the shear stresses.